Hello all, welcome to the video for section 2.3, the characterization of invertible matrices. We're going to open with a very long theorem. Okay, it's called the invertible matrix theorem. It gives, so let A be a n by n matrix. All of the following statements, there's lots of them, 3, 6, 9, 12. All of the following 12 statements are equivalent, which means if one of them is true, they're all true. If one of them is false, they're all false. So we'll start listing off these statements. The first is that A is invertible. Okay, so all of these statements are equivalent to A being invertible. A is row equivalent to the identity matrix. I think we mentioned this, must have mentioned this last time. A has n pivots, and you could say, David, this is pivot columns or pivot rows. But since it's n by n, it'll be both, or neither. Okay, the equation AX is equal to 0 has only the trivial solution. So now, the next one is that the columns of A form a linearly independent set. The linear transformation that takes X to AX is 1-to-1. But some of these implications we've seen as theorems previously. Like we saw that these two being equivalent was true, but we're collecting all of them together in one big theorem. The equation AX is equal to B has at least one solution for each B in Rn. The columns of A span Rn, and the linear transformation that takes X to AX is onto. So these three are all related outside of this theorem, but what's surprising is that they're also, so the transformation being onto and the transformation being 1-to-1, those are equivalent for an n by n matrix. That should be surprising. That should be a little bit surprising. And there's more surprises, right? So the statement J, there's an n by n matrix C with the property that AC is equal to the identity matrix. This isn't that surprising, but we're expecting that we need an inverse on the, or we need that this equality is also true, that CA is equal to the identity. And what we're seeing here now is that no, actually, as soon as one of these multiplications is the identity, the other one's got to come for free too. And that's our statement K. So as long as you're talking about an n by n matrix, square matrix, then having a inverse on one side is enough to show that it's invertible. And it doesn't matter which side. That's what K is saying. And then finally, the last, for me personally, the least interesting of the bunch, that the transpose is invertible. Okay, fine. So let's look at a simple example of applying this theorem. We want to show this matrix is invertible. So then really we could try and pick our favorite one and show that it's true. So we could show that it's row equivalent to the identity matrix. We could show that there are 3 pivots. There's lots of things we could try and do. I think we'll go with pivots since that requires not so much work. So let's row reduce A and see. So we'll row reduce. And count as pivots. Okay, so then A is equivalent to what? Let's do, oops. Row 3 minus 2 row 1. 1, 2, 3, 0, -5, -2. So 1 minus 2 is 0. -1 minus 4 is -5, and 4 minus 6 is -2. Okay. Look at this. Now we'll do row 3 minus row 2. 1, 2, 3, 0, -5, -2, 0, 0, 0. We now have at most, or really exactly, 2 pivots. So since we don't have 3 pivots, we can't be invertible. Alternately, we know that since we don't have a 1 here, we can't possibly be row equivalent to the identity matrix. In either case, either case, IMT, this invertible matrix theorem says our matrix is not invertible. So since A does not have 3 pivots, by IMT, A is not invertible. Boom, done. Sorted out. All right. All right. Let's talk also about invertible linear transformations. So if A is an n by n matrix, we can define the linear transformation T that takes x to AX. We say that T is invertible when there is a linear transformation in the other direction. So T goes from Rn to Rm. We want a linear transformation reversing T, going from Rm to Rn, with the property that if we first do T and apply that to X, and then do S afterwards. So if we take X, apply T, and then apply S to it, the net change should be nothing. We should get back to X again. And same if we start with, an X in Rm, and then apply S, and then apply T, we should get back to where we began. So if we take X, apply S to it, apply T to that, we should still get X. This is for each X in Rn. Sorry. What am I doing? A is an n by n matrix, so this should be from Rn to Rn. And so should S be from Rn to Rn. Okay. We should still think of it as going over and then back. But since A is an n by n matrix, there's no m here at all. Okay. Yeah, and so in this case we write that S is equal to the inverse of T, just like we do with inverse matrices. We have a little theorem that says sort of the obvious thing, that the relationship of T being invertible and A being invertible is very closely related. So theorem 2.9 says, let T from Rn to Rn be a linear transformation, and let A be its standard matrix. The transformation T is invertible if and only if the matrix A is also invertible. In this case, the linear transformation S of T inverse is given by A inverse X for all X. It's the unique transformation that satisfies these two equations that we need for S to be the inverse of T. Okay, and let's do a quick proof sketch why this is the case. So we've got an if and only if, so we should assume T is invertible and then show A is invertible, and then assume A is invertible and show that T is invertible. So if T is invertible, then T inverse is also a linear transformation. With standard matrix B, let's say. And so we know T inverse X is equal to X. But we know what this left-hand side looks like. Applying T inverse is just applying the matrix B. And applying T is just applying the matrix A. But this means that A has this is true for all X in Rn. And so we get that AB is actually equal to the identity matrix. And so by IMT, A is invertible. Because all we need is a single inverse on one side, and the whole thing is invertible. Okay, so now we should assume if and the reverse direction is in the textbook. The idea is just that if A is invertible and we apply this to T, then the two A's cancel, we get back X again. Okay, see the textbook for details. Let's go over another example. If T from R2 to R2 is given by this equation, So the linear transformation, we want to show that T is invertible and to find its inverse. So maybe you've done so many of these that it's perfectly clear what the standard matrix for T is, but in case it's not, let's go over it again. But we can find T's standard matrix. Oops. We can find the standard matrix for T just by applying T of E1 and T of E2. So if we sub in 1 for x1 and 0 for x2, we just get back -5, 4. T of 0, 1 is going to give us back 9, -7. So this implies that T of x is equal to -5, 4, 9, -7, x1, x2. Okay, and so this is our standard matrix A. So now the determinant of A is -5 times 7 minus 9 times 4, which is something terrible, right? Oh, sorry, this is a -7. So this is 35 minus 36 is -1, which is non-zero. This means that A is invertible. And A inverse is equal to 1 over the determinant. And then what we want to do is swap the main diagonal and negate the off diagonals. So exactly getting back 7, 9, 4, 5. Okay, and so that means T inverse of x is given by 7, 9, 4, 5 applied to x1, x2. Boom, done. Okay, I'll see you next time for section, where are we at now? 2.3? 2.4. Yeah, take care, everybody.